Hello and welcome back. This section is about choosing a convergence test. In previous section, we presented method for determining whether an infinite series converges. And in some case, we were able to discover that it is possible to determine the exact value of a convergent series. So in this section, we step back and focus on general strategies for classifying infinite series and deciding uh, which tests are appropriate for a specific series. So let's jump on. Categorizing the series. The first step in approaching an infinite series is to note some of the distinctive properties that help to classify it. Is it a series with positive terms, an alternating series, or something more general? Does the general term consist of rational functions, exponential functions, or factorials? Can the series be simplified in any obvious way before applying convergence tests? So let's jump on the first example. Discuss the series sum from k is equal to 1 to infinity, 2 to the power of k plus cosine of pi k times square root of k divided by 3 to the power of k plus 1. So, if you look at this series, the best way first is to split to two series because we have a positive in between them, right? First step is to split it into two series, right? And of course, to do that, that should not be something difficult to do. We have f sum from k is equal to 1 to infinity, 2 to the power of k plus cosine of pi times k times square root of k divided by 3 to the power of k plus 1 will be what? The sum from k is equal to 1 to infinity, 2 to the power of k divided by 3 to the power of k plus 1 plus the sum from k is equal to 1 to infinity, cosine of pi times k times square root of k divided by 3 to the power of k plus 1. And if you look at these two series, the first one is, this is a geometric series, right? And looking at the second one, because of cosine of pi k, you can see pi k, if k is 1, we have a negative 1. If k is 2, positive 1. If k is 3, negative 1. So we can say this is what? An alternating series, right? Right? So the general term of the first series, which is a ratio of exponential function. So this series is geometric series that can be evaluated explicitly. But the second series, because of pi k, cosine of pi k is same thing as negative 1 to the power of k. So we see that the second series is alternating series whose convergence also can be tested. But this series is convergent only when both. So we know first the original series is convergent only if both the geometric series and alternating series converge. So now, how do you test this one? Almost, without exception, the divergence test is the easiest test to apply because it requires nothing more than taking a limit. Further, it can lead to a quick conclusion, namely. So the easiest way in this case is, you know, the divergence test is the easiest test to apply, right? Because it requires taking only a limit. Okay. So after that, now let me give you the table for some spatial series and convergence test. So you have this table. Please take your time, read and understand them. Okay. You have geometric series, the condition of convergence, the condition for divergence, and the comment. So read everything, pause the video, read, take a note if you want, and then we would start the first example from there. So let's start. The first example. Does the series sum from k is equal to 1 to infinity, 1 minus 10 divided by k to the power of k converge or diverge? So let's jump. Solution. So you can see the term of this series will be alternating, right? Yeah. Yeah, for k less than 10. So we can see the term for this series alternate in sign for k less than 10. Why? Again, you can see if k is less than 10, this sign would be positive and negative because of this power, right? If the power is even, it will be positive, but if the power is odd, it will be negative. And after that, the remaining term will be positive, right? because it will be less. After k is less than 10, if k is greater than 10, it will be or equal to 10. This term will always be positive, and then remain positive. And close to 0 for k greater than 10. So which means applying the divergence test, we evaluate the limit of the general term using L'Hopital rules. So using L'Hopital rules, we can find this thing. So let's apply the divergence test. We evaluate the limit of the general term using L'Hopital rule. So if you use L'Hopital rule, we will find what? The limit of 1 minus 10 divided by k to the power of k as k approaches to infinity will be what? E to the power of negative 10, which is different from 0. So because the limit of the general term is non-zero, we conclude what the series diverges. It's close to 0, but not 0. So the series diverge. But it will be very slowly because it's close to 0. So identify special series. We have studied several special family of series that are readily identified and analyzed for convergence. So you should look for geometric series, P series, and less obviously and less common telescoping series as well, okay? So for our next example, does the series sum from k is equal to 4 to infinity 1 divided by 4th root of k squared minus 6k plus 9 converge or diverge? So let's start this one as well. Solution. First thing, the divergence test is can we do the divergence test in this one? No. It will be inconclusive for this series of positive term because the series is a positive term, right? This is a so I know this is a series of positive terms, right? So, if I use the divergence test, the limit will be 0, right? But that will be inconclusive because divergence tests cannot be used to prove convergence. So that's why we will not use divergence tests here. Okay, let me write the divergence test will be inconclusive. Parentheses because cannot prove convergences. Okay, that's why we do not use divergence tests. But a good step in this one is to rewrite, you know, this series. So rewrite this series. How do you rewrite it? We have the sum from k is equal to 1 to infinity of 1 divided by 4th root of k square minus 6k plus 9. And we can see this is same thing as the sum from k is equal to 1 to infinity 1 divided by 4th root of k minus 3 square, right? And of course, we can use substitution. Shift the index. Let j be equal to k minus 3. So we know then that will change the index of this one also. So it will become when, sorry, k start from what? On the original problem, k is 4. Thank you, sorry. I'm using 1. K is 4. So if k is 4, then g will be what? 1. So that will make my series g is equal to 1 to infinity 1 divided by 4th root of j to the power of 2. All right. And of course, we can see square and 4th root will simplify. So simplify. We'll get what sum. I told you if you want, you can change your j to k once you do your substitution. 1 divided by square root of a. And what type of series is this one? This is a P series, right? So now we identify as what? This is a P series with, what is your P? 1/2, which is less than 1. Therefore, it diverges, right? Because it's only converse, P series only converse if P is greater than 1. Any questions so far? Now for this example, we have that's the series sum from k is equal to 1 to infinity, k square of k squared times e to the power of negative 2k converges or diverge. You know, this is exponential. So the general term of this series of positive term can be integrating using integration by parts, right? If you look, we can use integral in this case. So again, my a sub k, which is k should be equal to f of k, which is what? K square e to the power of negative 2k. So we'll set our f of x is what? X squared times e to the power of negative 2x. So now, because the general term of this series of positive term, positive terms can be integrated, right? Can be integrated. And to integrate this one, we can use integration by parts. So that's why we'll start from 1 to infinity x squared e to the power of negative 2x dx. You know how to do this one, right? So because we have done so many times this type of integral, I will just give you the steps. So use what? Integration by parts. How many integration by part do you have to do twice? And then you will see this integral 1 to infinity x squared e to the power of negative 2x dx. You will see the answer will give you 5 times e to the power of negative 2 divided by 4, which is less than infinity. So because the integral converges, we can say what? The infinite series also converge. Also converges. So we could also use what? We could use the ratio test, right? We could use also the ratio test. I know some of you were thinking about that. We could use the ratio test. Because the ratio test, we will have what? Finding the limit like for the ratio test, we will do the limit k plus 1 times z squared times e to the power of negative 2k plus 1 divided by k squared times e to the power of negative 2k as k approaches to infinity, which is, if you simplify, you will get what? E to the power of negative 2, the limit k plus 1 divided by k squared as k approaches to infinity, which is e to the power of negative 2 times 1, because this limit is what? 1. This limit is 1, right? And then we can see, because the ratio of successive terms in less than 1, then we conclude what this series converge. Okay? Last, not the least, so we have, does the series sum from k is equal to 2 to infinity of cube root of k squared minus 1 divided by k to the power of 4 plus 4 converge or diverges. So, again, solution. So if you look at this one, the divergence test is inconclusive again. Is inconclusive. And ruling out the integral ratio and root tests as impractical. So you cannot use those one. We are left with a comparison test. The end behavior of the general terms is to determine by working with the leading term. So you can see, let's we can use comparison test, right? So first thing, we know we have cube root of k squared minus 1 divided by k to the power of 4 plus 4, which is approximately equal to what? Cube root of k squared divided by k to the power of 4, which is equal to 1 divided by k to the power of 2 thirds, right? So therefore, a good comparison series is sum is equal to 1 divided by k to the power of 2 thirds. And you know which is a divergent P series because P is less than 1. So the ordinary comparison test is difficult to apply in this case. Wow. Why? Because, this will be my B sub K. So, yeah. So even the comparison test is, this happens sometimes, okay? Then now we have to use to apply in this case. Why? Again, I'm going to put y in parentheses because this is my B sub K. Because you can see B sub K is greater than A sub K for K greater than or equal to 3. That is, 2. You can check. So we cannot use the comparison test. So since we cannot use the comparison test, we are left with what? The limit, right? So we are left with only the limit in this case now. So let's use